My name is Rick Sasso, and I am very excited to present this Orthodome video entitled AI Through the Continuum of Care. We are just in the infancy of the AI transformation of healthcare. Today, we will walk through how AI can be applied to spine care, in particular, how it can be used in imaging across the care continuum. Over 90% of medical data is in the form of unstructured medical imaging data. The knowledge gained by structuring that data will most certainly revolutionize how we make clinical decisions. First, what is AI? You can think about a convolutional neural network as a series of algorithmic layers, each optimized to detect distinct structures and features on a medical image. Based on its success in finding that structure on a training dataset, it's given a weighting. The resulting weighted network of algorithms, or neural network, can then be used to perform different tasks. The first step in image processing is a binary segmentation, determining what is bone and what is not bone. A layer deeper is a semantic segmentation, or multi-class segmentation, where every pixel in the image is assigned to a class or structure. The resulting labels and landmarks on the volumetric dataset are then used to automate the measurement of anatomic structures, and from the measurements we can infer diagnoses and plans. At its core, AI turns unstructured imaging data into easily accessible and structured data sets of biomarkers that can be related to the patient record. For instance, in diagnostic imaging, AI can be used to quantify anatomic structures in pathology. In surgery, it can be used to quantify intraoperative imaging, automate planning, and power surgical navigation. By applying it to post-op imaging, an automated measure of the surgical result can help us quickly see if we've met the surgical objectives and to track the patient longitudinally. When applied to diagnostic lumbar MRI images, the technology can perform a series of automated measurements on key anatomic structures. These measurements are used to derive a structured data set of objective and quantifiable biomarkers. We'll first identify the vertebral levels, which allows it to categorize subsequent findings. The quantification of anatomic structure starts with thecal sac area, a linear distance measurement in the lateral recess, and perineural fat and nerve for evaluation of nerve compression. The disc is also quantified, including height measurements, volumes of the nucleus and annulus, and pixel brightness representing hydration within those structures is assessed. Alignment parameters on the MRI can be computed looking at lumbar and segmental lordosis and spondylolisthesis. A measurement of disc herniation outside the end plates is also computed. The result of this analysis is a structured dataset of key pathology biomarkers that can be saved to the patient record and used for population analytics. AI can also be used to assist with intraoperative navigation and robotics, in this case, a unique holographic guidance system. First, the guidance system uses AI to process the intraoperative 3D image, performing a 10-class segmentation, which automatically identifies the pedicle, lamina, and additional structures. Once the pedicle is identified, the next AI network in the pipeline performs screw planning. The AI selects the entry point, endpoint, trajectory, length, and diameter of the screw based on a surgeon preference for pedicle fill. Now that the intraoperative image has been segmented and planned, this data can be visualized in the holographic display, which projects a 3D image superimposed on the patient. The segmentation dramatically improves visualization of the anatomy, as it displays only the relevant anatomic structures that the surgeon wants to see, minimizing noise, artifacts, and extraneous information. The screw trajectory is also visible within the anatomy, such that the surgeon has guidance information overlaid on their real instruments in the surgical field. The AI-generated data from the diagnostic scan and surgery can be used for population analytics. In this example, over 4,000 patient MRIs were run through the AI, generating over 2 million biomarker data points in and under 10 hours of processing time. Without AI, this information would take a human years to generate. The population data can then be grouped by anatomic level, run against demographics. It can be used to compare individual results against population statistics and, of course, be related to pain and patient-reported outcome measures. Over 90% of medical data is in the form of unstructured medical imaging data. The knowledge gained by structuring that data will most certainly revolutionize how we make clinical decisions. The insights that we will gain from AI processing image data will be nothing short of revolutionary. We have only just begun to structure the vast quantities of data currently languishing in the PACS.